Hey guys, just wanted to welcome you back to our review video over pH concepts, last part of this acid-base unit, so hopefully you guys get a lot out of this. So just a couple things to keep in mind about acids and bases. Remember that acids start with that hydrogen, right? And bases, they can end in OH, they don't have to, but typically what we look at, remember that acids are proton donors. So it's going to donate that hydrogen, and bases are proton acceptors. I'll get my handwriting right good one of these days. So we need to think about these things in solution. If we have more H than OH, okay, remember when we talk about H, means kind of the same thing as hydronium, H3O+. I'll refer to it both ways in this video. If we have more H than OH, that tells you that this is an acid. More OH tells you it is a base. And if we have equal amounts, it is neutral, right? Neutral being something like water, H2O. So that gives us some interesting things that we can talk about and some interesting things that we can kind of think of when we think about acids and bases. So we can think of actually water as self-ionizing. Remember, water is amphoteric, meaning that it can be an acid and a base. So if I look at this following situation here, I've got two molecules of water. In this situation, one molecule of water donates the hydrogen to the other. So water is acting as an acid, at least this one is your acid, and this is your base. Remember, acids donate protons, bases accept them. So here what we end up with is H3O+ and OH-. Now notice the double arrow here. The double arrow here means that this is in equilibrium. And that's something that's really important, because if it's in equilibrium, then we can come up with a formula, an equilibrium expression, like we did our last unit, to know that if we have hydrogen concentration, we can figure out the OH concentration, because the equilibrium constant for water is always 1 times 10 to the negative 14th. So we can plug in numbers and then be able to solve very, very easily. Okay? So a couple things you may want to think about as you go through and do some of these types of problems. We talked a lot about acids before, and all we're going to look at is strong acids and bases. Now, if you remember, if those acids are strong or bases are strong, you get 100% dissociation. Well, what does that mean? What that means is that if I have something like this, 2.45 times 10 to the negative third molarity of HCl, and it's asking me to solve for OH, this essentially completely dissociates. So when I'm in solution, that means that I get 2.45 times 10 to the negative third H, or H3O+. If it 100% dissociates, it means it all breaks apart. So I'm going to have 2.45 times 10 to the negative third concentration of H, as well as 2.45 times 10 to the negative third concentration of Cl-. Okay, it 100% dissociates. So if I know this information, I can then plug it into the expression above and solve for my OH concentration, which is what the question is asking for. Kw 1.00 times 10 to the negative 14th equals H concentration, so 2.45 times 10 to the negative third times my OH minus concentration. Now all I do is divide on both sides. And I get my OH concentration. And what I get is 4.08 times 10 to the negative 12th. And remember, it's concentration, so we're looking at molarity. Okay. So pretty straightforward there. But the problem with this is that those concentration numbers are very hard for everyday people. I mean, we're scientists, so we totally get this. This is super easy for us to know the difference in concentration here. But for the common public, the hoi polloi, if you will, if you don't know that term, look it up. Basically, the status quo, we need something that's a little bit easier for them to understand. So what we have here is a scale. And we use a logarithmic scale called the pH scale. And you've heard of this quite a bit. We've talked a lot about this in the past as well. The pH scale gives some meaning to those numbers. Makes it a little bit easier to understand. So we have numbers that go from a scale of 0 to 14. 0 meaning the most acidic, 14 being the most basic, and then 7 being right there in the middle as neutral, pure water. So you have a variety of different things here that may help you kind of visualize it or see it. You've got upset stomach acid, normal stomach acid, orange juice, tomatoes, seawater, milk of magnesia, borax, bleach. You get the idea here. But it makes it a little bit easier to figure out. So how do we go through and actually calculate this? Well, if we scroll down here, we have our formulas. And these formulas are really important to know. Now, again, you'll be given these formulas, but make sure you know how to use these 5 formulas here. So in order to get the pH, we just take the negative log of the H, or hydronium concentration. POH, negative log of our hydroxide concentration. The concentration of H is equal to 10 times 10 to the power of negative pH. It's an inverse function of a logarithm. Same with OH, 10 to the negative POH. And pH plus POH equals 14. So if I'm looking at the scale itself, pH scale runs typically from 0 to 14. There are exceptions. Where anything below 7 is an acid. Anything above 7 is a base. And anything at 7 is neutral. One other thing I want to make sure that you understand is that this is a log-based scale, so the difference between 6 and 7 is tenfold. What that means is that something with the pH of 6 is 10 times more acidic than something with the pH of 7. And that trend continues. So if I'm looking at 4 and 6, that is a 100-fold difference. Meaning that something with the pH of 4 is 100 times more acidic than something with the pH of 6. So let's do a couple of practice problems, and then we will call it a day. All right? Let's take a look here. What is the pH of a 0.0235 molar HCl solution? Well, let's think about what we're looking for here. We're trying to solve for pH, so we have all those formulas there. We're given the concentration of HCl. Well, remember, everything I'm going to give you is strong for the time being. We'll study weak acids and things like that when we get to AP Chem. But this is the same as the concentration of H, right? Because it completely dissociates. So 0.0235 is my concentration of H. So now all I do is I just take the negative log of 0.0235. And I get my answer. I get my answer of 1.63. Very acidic. Okay. What is the pOH of the same solution as up above? Well, we could go through and do more math here and figure that out. But remember that pH plus pOH equals 14. So I just plug my number in. 1.63 plus X is 14. What I get is 12.37 for my pOH. But again, it's all just about thinking about what information I have and what equations am I going to use to solve. Last 2 problems we're going to look at here. It says, what is the pH of a 6.50 times 10 to the negative 3rd potassium hydroxide solution? Well, the question's asking for pH, and it gives me this for KOH, so I can actually safely say that this is the concentration of OH. So there's really one of 2 ways I can do this. I can solve for pOH and then get pH from that using the pH plus pOH equals 14. Or I can plug this into my KW expression. 1 times 10 to the negative 14th equals H times 6.50 times 10 to the negative 3rd to get H, and then take the negative log of that. So there's multiple ways that you can go through and solve each problem. I'm going to go ahead and solve for pOH. because I think that's going to be a little bit easier. So I just plug that number in there and solve. So I get a pOH is 2.19. And then I'm just going to use the same formula before. pH plus 2.19 equals 14. So I'm going to get 11.81 for my pH. Quite basic. Okay. Next question says, what is the pH, pOH, H, and OH of a solution when 25.5 grams of HCl are added to 450 milliliters of water? Well, this doesn't give me concentration. It doesn't give me molarity. But if I remember from a long, long time ago, molarity is moles per liter, right? And I can convert HCl to moles, 25.5 grams of HCl, grams to moles. Where do I find that information? I guarantee you just said periodic table. I can get my moles. Is it 0.70? $450 milliliters. It's 0.450 liters. I can get my molarity. It's 1.55. Remember, that's HCl. So that's going to be the same as my H concentration. Now I can pretty much solve for everything else, right? So I've got my H. Let's get pOH from that. I'm sorry, let's get pH from that. .19, so very acidic. pOH, easy to get from that. 14 minus that, so it's going to be 13.81. Highlight my H concentration too. And now I can get 10 to the negative 13.81 is going to give me my OH. So a lot of times it's just using a combination of these to be able to solve for what we're looking for. So my OH concentration here is going to be 1.55 times 10 to the negative 13th. And again, molarity. All right, 13. Okay. So again, just plug those numbers in and solve, guys. It really is not that bad, all right? If you have questions, let me know. Have a great day, and we will talk to you later. Bye-bye.